Hi girls. In the last class we have discussed about properties of binary tree, and today we are going to discuss about binary tree ADT, that is abstract data type. Okay, and how to implement a binary tree in uh, reality. I mean, like in our programs, right? So binary tree abstract data type, what does it contain? See, it includes these operations that can be performed uh, on a binary tree, which is a short in short form we call it as B tree, right? See, first we are declaring a binary tree. Next, we are creating a make a binary tree. Next, we are checking whether it is empty or not, and next we are trying to fetch the left child, next right child, and also the data in that binary tree, which is called the element. Okay, next we have some methods which can be performed on that binary tree, like is it empty, um, next left child, again create a which these uh, what you say elements. I mean, these values can be passed as values to these methods. um, is empty, left child, you can create a left child, you can create a right child, and left child, from the left child you can create a B tree again, and again you can create a right child. You can create a B tree from another right child, and what is the data that has to be stored in that particular binary tree. So these are all the uh, elements or things which can be included in an ADT, like that is abstract data type. The six functions with their domains and ranges are from 1 to 6. See, so these are the functions with their domains and ranges. And next, 17 to 14 are the functions which are related to these uh, domains and ranges. Right? How we can use this values into our methods. Next, yeah, the what does the create operation do? The create operation creates an empty binary tree. So no nodes are present in the tree. It just creates a binary tree which is empty. That means there are no nodes in that tree. And this is empty operation is used to check whether B tree is empty or not. So whether we have any want to check whether the tree is empty or it has any nodes or elements in it, then you will be using this method is empty, and which will give you which will give a boolean value that is true or false, which returns a boolean value that is true or false. And again, this is empty method can be used on the left child and the right child, and if you use this left child B tree and right child B tree, it will give the subtrees of the root and each subroot. So see, for example, you have a tree. So this is the tree, this is the root, it has two subtrees, and this is the root for these two, and this is the root for these two. So in that manner you can check for the I mean left and right subtrees by using this method, left child and right child of the B tree. Next, data of B tree returns the data element stored at that particular node. Okay, apart, what is the purpose of creating a binary tree? To store the data, right? So we are storing the data here inside, which is called the element. So that can be retrieved by using this data method, data of B tree, which will give you the data element. So this is how the program code looks like. So you will have two classes, one as tree node, and each node in a tree will have three things. One is data, which is declared as character data type, and the other has two, that other two are pointers, left child and right child, which point to the subtrees or the children of the node, or of the children in that subtree. Next, you have a class called binary tree. We'll create a node called root. Okay, tree node. So if root is equal to null, you'll check that, you will tell that a tree is empty. Uh, if you use this tree node, get node, you on this tree node, you can uh, check whether it is what node it is, like what element is there. Next, you can insert node, you can delete node. All these are pointers, right? Okay. Yeah, so this is about the binary tree abstract data type. So these are the ranges and functions which can be passed as values to these methods, right? Next, yeah, what are the operations that can basic operations that we can perform on any binary tree? First one is creation, to create an empty binary tree to which the root points. So there is only root, I mean there are no sub, what you say, children to that root, so it is an empty binary tree. Next, traversal, visiting, I mean traveling from one node to the other node, traveling from one node to the other node, so visiting all the nodes in a binary tree, it is called traversal. So how you travel from one particular node to that leaf node in the last level, so this is what is called traversal. Next, deletion, if you want to delete any particular node from a non-empty binary tree, then you can do this operation. Insertion, inserting a new node into the binary tree, if even if it is empty or not empty. Next, merge any two binary trees and combine. Next, copy a tree from one tree into the other tree. Next, comparing two binary trees. Okay, you can compare any two binary trees. Next, finding a replica or mirror of a binary tree, that you can find the replica, I mean the same shadow of a binary tree, you can uh, find it out. So these are all the operations that you can perform on a binary tree. The most important are creation, traversal, insertion and deletion. So these are the four operations that we perform regularly on any binary tree. So how to implement a binary tree? Yes, we can implement. Realization of a binary tree is nothing but implementing the binary tree in actual, or what you say, program. Yes, how do you implement? See, the implementation of a binary tree should represent the hierarchical representation between a parent node and its left and right children. So we should be able to properly represent the children and their relation with the parent uh, in the hierarchical manner, how they are related to each other in the best possible way. So the best way to represent binary tree is linked storage. Okay, I mean linked list. By using linked list, binary tree can be represented in the best form. Next, the linked structure is more convenient for insertions and deletions. The drawback of sequential organization is the insertions and deletions are very complicated in sequential, I mean that is arrays, sequential representation of data. So that is the reason we go for linked list. Okay, so that reason applies here as well, that linked list structure is more convenient for insertions and deletions. But we will see how we can implement in binary trees, how we can implement binary trees in arrays, and as well as how implementation of binary trees is more um, convenient in linked list. So this is we will see here in this class. So array implementation of binary trees. So how do we represent binary trees with the help of arrays? See, for example, if we take a tree, complete tree in the sense all the children have nodes, I mean a node has at least two children, or it should be the leaf node. Okay, so it is called a complete tree. I mean, it can't have only a left child, or it can't have only a right child. So it will have all the nodes completely. Next, a complete binary tree of height h has 2 power h plus 1 minus 1 nodes. So if you take a complete binary tree whose height is h, the number of nodes present in that particular tree will be, you can calculate that by using this expression 2 power h plus 1 minus 1. For example, if you take 2 as your h, I mean height of the tree, then 2 plus 1 is 3, 2 power 3 is 8, and 8 minus 1, 7. So on the whole, you will be having 7 nodes in that particular tree. So this is a complete binary tree where each node has where each node is having 2 children, right? Next. So when you represent when you want to represent a complete binary tree of height h, that is, it has having these many nodes, then the array size should also be the same. That is the number of nodes which are there in the tree. So you have to create an array of that size to store all these nodes of that tree. Next, how do you decide the location of any ith node in a tree? These are the roots that you have. See, if any node with index I, where I is greater than 0 and less than n minus 1, you can say whether it is a parent or left child or right child depending on these conditions. So it is a parent if that t minus 1 by 2 if I is equal to not equal to 0. If I is equal to 0, then it is a root that has no parent. If it is not equal to 0, then it is a subnode or child of a root, and it is a parent to other nodes, right? Next, left child. If you want to decide whether it is having a left child or right child, then you will use this expression 2 into I plus 1. If this 2 into I plus 1 is less than or equal to n minus 1, it has a left child. If this 2i is greater than or equal to n, then I has no left child. So if it is 2i plus 1 is less than or equal to n minus 1, then it is the left child of a particular in that tree. If it is greater than n, then that I has no left child, that ith node is not having any left child. In the similar manner, right child, if 2 into I plus 2, if 2i plus 2 is less than or equal to n minus 1, it is the right child. If it is greater than or equal to n, 2i plus 1 is greater than or equal to n, then I has no right child. So this is how, by using these expressions, you can conclude or you can make a conclusion that there are, whether it is a parent node for any children, or if it is a left child, it is having left child or not, it is having right child or not. I mean that itself is the leaf node for that particular node. Next, see, this is how this complete binary tree is represented in this form of an array, in the form of an array. See, for here we have 7 elements. You have to take an array of size 7, and see, so root will be the first element that is stored in the array. Next, the children of the root, BE and their subchildren, so CD and FG, right? So we have taken an arbitrary. Next, as there are no nodes further, we are leaving these two nodes as empty. I mean, these nodes are not having any children. Next, tree with 11 nodes. See here, most of the nodes are concentrated in the left part of the tree. So how this is represented by using an array? See, A, B, C, D. So A is having two children. So B, C. Okay. So B, C, right? Next, B is having two children, D, E, but C is not having any children, so we have left them empty. Next, D is having two children, F and G, and E is having two children, H and I, and further there are no children exist, so you are leaving them in the next positions in the array empty. So the height of this tree is 3, right? 1, 2, 3. So 7. So this is not a balanced tree. So this has given rise to these empty positions. So these will consume a lot of memory, which will cause in the wastage of the memory. Next, for a skew tree, it is much more see wastage of memory. See here, A B B is not A is not having any subchild, only one subchild CB, so we have left that position empty. Again C, B is having only one child subchild, okay, so only for that, so is again that we will be leaving 3 positions as empty. Next, C is having only one child, so the other traverses, like you will be giving place for these also, which are actually empty nodes. If there are no nodes actually here, but you will be leaving place for them also to actually represent the correct position of the node in the tree. So if you don't leave this empty spaces, it will be like B. If you store C here, it will look like C is on the same level as B, but it's not true. It's on the other level, right? And again, C is not having the right subchild. It is having only left subchild. So because of these reasons, we will be leaving these nodes empty. So these nodes which are absent on the right side, for that also we have to show um, the we have to allocate the places though they are empty. So here there is a lot of unused space here. So a lot of unused space is there because of the binary tree representation using arrays. So only for a complete binary tree, no wastage is there. Okay, no space is wasted. Okay, but for other trees like these, a tree with which unbalanced, it is not a complete tree. It is the more nodes are concentrated on the left side of the tree, and like skewed tree, right left. This is a left skewed tree. So in such cases, more amount of memory is wasted. See, all these places are left empty because to properly represent the level of these nodes. So see, for the skewed tree, half of the array is only used and more is left unused. So this is the reason we say that arrays are not that much useful for the representation, or that arrays can't represent the binary trees in a perfect manner, like linked list, right? Insertion and deletion is also very much difficult with this representation of binary trees using arrays. So what are the advantages? See, the advantages of creating binary trees using arrays is any node can be accessed from any other node by calculating the index. So you can access any node in the tree by calculating the index of that particular node from the place where you are by using the present node's index. Next, the data is stored without any pointers to its successor or predecessor. Yes, as in linked list, we have to store the what to say, links, pointers to the next nodes. So here such overhead is not there. So pointers, no need to store any pointers to its successor or predecessor. Next, in programming languages where dynamic memory allocation is not possible, like BASIC and Fortran, we can represent arrays only by means, array is the only means to store a tree. So there you can use only array to store a tree in languages like BASIC and Fortran. What are the demerits? Yes, other than full binary trees, complete binary trees, majority of entries will be empty. Next, it allows only static representation, like you have to declare the size of the array beforehand. You cannot change the size during the execution. No dynamic memory allocation. Next, inserting a new node or deleting a new node will be very much difficult because of the movement of the data up and down in the array. So it will result in excessive consumption of the processing time. So that is the reason the most useful or most comfortable representation for binary trees is by using linked list. Yeah. So how to represent a binary tree using linked list? So binary tree has a natural implementation in linked storage. So naturally the binary representation of a tree looks similar to the representation of a linked storage. So see, we in linked organization, the nodes can be allocated dynamically. The nodes the nodes can be allocated storage dynamically as and when needed, and each node will have two fields. Apart from the data field, you have two other fields, left child and right child. So each node of a binary tree has both a left and a right subtree. So each node will have three fields, one for data and the other for the left pointer to the left child and right child. The other two are pointers to the left child and right child. So this is how it looks like in the form of a tree. Next, so a node does not provide information about the parent node. Okay, so this will not have information regarding whose from where it has spanned, I mean whose child it is, but still you can, it is more comfortable to use linked list for the representation of binary trees. If needed, you can add a fourth field in the node called parent field. Okay, if it is required for your calculations. Next, the root of the tree is stored in the data member root of the tree. So the root is stored in the data of the node from where the actual tree starts. So this data member provides an access pointer to the tree. So this, see here, this is how it is represented. It actually points, this root is stored in the as a data member of the tree of this node. This will point to the starting of the tree, right? See here, 0 stored at left child or right child represents the respective child is not present. So if you see here, for in these nodes, here it is set to 0. Here we are filling them with 0. The fields here are filled with zeros. That represents that these are the leaf nodes, and also they don't have any children further, left child or right child. In this node structure, left child or right child are the two link fields to store the addresses of the left child and right child of a node, and data is the information content of the node. So L child and L R child are what? Link fields. They are links which will store what? Addresses of whom? Left child and right child of a node where we are present. Yeah. Next, with this representation, if we know the address of the root node, then by using it we can move on, or we can access any other node in the tree. So each node of a binary tree, which is nothing but, see, if we consider this node, it is a node in this tree, but it is a root to this subtree. And for the whole tree, this is the root, but for this subtree, this is the root, and for these two children, this is the root. So each node of a binary tree has both left and right subtrees, which can be accessed through pointers. So if you move on to from one node to the other node, so if I want to move from A to I, so how I have to traverse? By to B, then to D, and then to I. So we can through accessing the pointers, we can move from one node to the other node. So see here, this representation, linked list representation of this tree. So A has two children, so they are pointing to two different nodes, B and C, and B is also having two children, D and E. E is empty, link fields are empty, they are set as 0 because it has no children. Only D has two children, H and I, and H, I are all, link fields are also set to 0 because they are the leaf nodes, they don't have any children. In the same manner here also. See, if I left skewed tree, here you will be representing it like this. All the right link of each node is set to 0, right? So here no memory is wasted. So this is how you implement the functions, different functions in the tree. See, insertion of a node, deletion of a node, post order, in order, pre-order, how to calculate the height, how many leaves are there, how many nodes are there, breadth first search algorithm, traversal, depth first search traversal, okay, and the other operations that you can perform on any particular tree. This is how you can see here. This is how we do by using a program, right? Next, see how the physical representation and logical representation. So physical view, logical view of a tree will be. So this is our actual tree. This is how physically the nodes will be stored in our memory, and logically how it represents. See, here you have A as the root node, and you have values in the left child and right child. Left child is pointing to its left subtree, and right pointer is pointing to its right subtree. And when you have no subtrees or nodes for that particular node, you will be setting them to 0. So you can see how it looks like. So what are the advantages of using or representing binary trees through linked operations is, for unbalanced trees, the memory is not wasted. Though it is not a balanced tree, the memory is not wasted. Only as and when the node is added to the tree, memory will be allocated. Insertion and deletion operations are more efficient in this representation. So you can easily insert and easily delete the nodes in this representation of tree using linked list. Next, it is useful for dynamic data. I mean, as and when there is a requirement for the insertion of a node, you can insert or allocate the memory. Next, what are the disadvantages? No direct access to any node. So you can't directly access a node by using the index position. In arrays, you can directly access any node with the help of the index position. But here, if you want to reach to H, you have to go to you have to find out the root of the tree. From there, you have to traverse till H through other nodes. So direct access is not possible. Next, as compared to sequential representation, the memory needed per node is more. Okay, so for every node you have to allocate some extra piece of memory, because the left child and right child have to be pointed out with the help of two link fields. Apart from the data field, you have to store two more fields, that is left child and pointers to the left child and right child of the binary tree. So it requires more amount of memory. And the programming languages which do not support dynamic memory management, they have to use arrays only. When our language supports the dynamic memory management, then only we can use represent binary trees using linked lists. Next, how to insert a node at any node in a at any position in a binary tree. So first you will search for the node. It is a two-step process. So first you will be searching for the node where the child node has to be inserted. If it is at some level I, then the node which will be inserted will go to the level I plus 1, which will be either its left child or right child. So for this, if you take this tree, if you want to represent, if you want to insert a node here, you have to, what is the height, level of this node? It is 0, 1, 2. 2 is the level of this node. So your leaf will be added at the level 3. So you will be calculating the level where you have to add the node, and next link a new node to the node that becomes its parent node, that is either the left child or right child. So you will be linking a node here like this. Okay, so you will be setting the address of this node into the node to which it is linked. So this will become the parent for this node. So you will be setting the value address pointer of this node into the right part, because it is going to be the right child of this particular node. So you have to set the link field here as in this node, right? So this is about your binary tree ADT, abstract data type, and how you can implement trees using arrays and linked lists. If you have any doubts, ping me in the group, girls.